Imagine standing beneath a machine so tall it towers higher than a 25-story building. Steel cables hum above your head, containers the size of small houses glide silently through the air, and every movement carries cargo worth millions of dollars. One tiny mistake could shut down an entire port, delaying products that people around the world expect to arrive on time. But here's what nobody tells you. These giant container cranes aren't just machines. They're some of the most precisely engineered structures ever built, and their journey begins long before they ever reach the waterfront. Think about this. A single modern container crane can weigh more than 2,000 tons and lift containers weighing over 65 tons with astonishing precision. It must survive hurricane-force winds, relentless saltwater corrosion, and operate almost every day for decades. Most people only notice these giants from the deck of a ship or the window of an airplane. Today, you're about to discover where they truly come from, how they're built, and why every bolt and weld could mean the difference between flawless operation and catastrophic failure. We will travel from iron ore mines buried deep beneath the earth to enormous steel mills where temperatures glow hotter than flowing lava. You'll step inside factories where sparks explode like fireworks, robotic welders shape mountains of steel, and expert engineers measure parts with incredible accuracy. And this is where it gets truly extraordinary. By the end of this journey, you'll never look at a shipping port the same way again. Everything starts with one of Earth's most valuable industrial resources, iron ore. Much of the high-grade ore used to produce structural steel comes from Australia, Brazil, and South Africa, where enormous open-pit mines stretch for kilometers across the landscape. Some ore contains more than 62% iron, making it ideal for heavy engineering projects like container cranes. Imagine trucks taller than a 2-story house carrying hundreds of tons of rock in a single trip. Before the first crane component even exists, this incredible journey has already begun. After extraction, the ore travels hundreds or even thousands of kilometers by heavy freight trains and massive bulk cargo ships. Some shipments cross entire oceans before reaching steel plants in China, South Korea, Japan, or Europe. Most people never think about this hidden supply chain, yet every crane depends on it. If just one link fails, manufacturing schedules can slow dramatically, affecting ports around the world. But iron alone isn't enough. Engineers also rely on carefully controlled amounts of carbon, manganese, silicon, chromium, nickel, and other alloying elements to produce high-strength structural steel. These materials improve toughness, corrosion resistance, and fatigue life, allowing cranes to withstand millions of lifting cycles over decades of operation. Every percentage matters because even a small change in composition can affect how the steel performs under extreme stress. The steel plates used in giant container cranes can weigh several tons each and measure dozens of millimeters thick. Manufacturers often select specialized structural grades designed for heavy construction and excellent weldability. Every plate receives identification markings so engineers can trace its origin, production batch, and quality records years after installation. Hidden inside every crane is a complete history written in steel. Another material plays a surprisingly important role: copper. Thousands of meters of electrical cables power motors, sensors, lighting systems, cameras, communication equipment, and automated controls. Much of the world's copper comes from Chile and Peru before being refined into highly conductive wire. Without these hidden networks, even the strongest crane would remain completely motionless. Environmental responsibility has become another major challenge. Mining, steel production, and global transportation generate significant carbon emissions. So many manufacturers now increase recycled steel content, improve energy efficiency, and adopt cleaner production methods wherever possible. Some modern structural steel already contains a high percentage of recycled material without sacrificing strength or durability. What happens next surprised even experienced engineers, because turning these mountains of raw steel into one perfectly aligned machine requires precision on a breathtaking scale. How the real transformation begins. Massive steel plates arrive at the fabrication plant, where every piece is checked against digital engineering models before a single cut is made. Imagine standing beside a plate weighing more than an elephant as precision CNC plasma and oxy-fuel cutting machines carve complex shapes with millimeter accuracy. Inside the factory, the air vibrates with the sound of cutting torches, glowing sparks shower across the floor, and the smell of hot steel fills the building. Every cut must be perfect because even a tiny error can multiply across a structure stretching more than 70 meters. Next, the plates move to powerful hydraulic press brakes and rolling machines that shape them into box sections, beams, and structural components. Some presses generate thousands of tons of force, slowly bending steel without cracking its internal structure. Workers constantly measure every angle because a difference of just 1 or 2 millimeters could affect the crane's final alignment. Think about this. Every section must fit together perfectly even though some components are longer than a city bus. The shaped components enter one of the most demanding stages: welding. Robotic welding systems and highly skilled welders join massive sections using high-strength welding wire, while electric arcs burn at temperatures above 6,000 degrees Celsius (10,800 degrees Fahrenheit). Bright blue-white flashes illuminate the workshop like lightning. Molten metal flows into every joint, and protective gas shields the weld from contamination. Some critical welds require multiple passes and careful cooling before inspectors approve the next step. The giant structural sections now move into an assembly yard large enough to resemble an airport runway. Towering lattice booms, machinery houses, legs, and support frames come together with precision lifting equipment capable of handling hundreds of tons at once. Hydraulic cranes slowly rotate each section into place while engineers communicate through radios, guiding every movement with incredible patience. Watching these enormous pieces fit together feels less like construction and more like assembling a giant mechanical puzzle. The giant structural sections now move into an assembly yard large enough to resemble an airport runway. Towering lattice booms, machinery houses, legs, and support frames come together with precision lifting equipment capable of handling hundreds of tons at once. Hydraulic cranes slowly rotate each section into place while engineers communicate through radios, guiding every movement with incredible patience. Watching these enormous pieces fit together feels less like construction and more like assembling a giant mechanical puzzle. Finally, giant electric motors, gearboxes, wire ropes, sheaves, sensors, cameras, and computerized control systems transform the steel structure into a living machine. Every cable connects to a carefully labeled control panel. Every motor undergoes rotation tests, and every movement is calibrated before the crane ever reaches a port. But here's where it gets truly extraordinary. Building the crane is only half the challenge. Proving it can perform flawlessly under extreme conditions is an even greater engineering achievement. Finally, giant electric motors, gearboxes, wire ropes, sheaves, sensors, cameras, and computerized control systems transform the steel structure into a living machine. Every cable connects to a carefully labeled control panel, every motor undergoes rotation tests, and every movement is calibrated before the crane ever reaches a port. But here's where it gets truly extraordinary. Building the crane is only half the challenge. Proving it can perform flawlessly under extreme conditions is an even greater engineering achievement. Now comes the moment when engineers ask a simple but critical question. Can this giant be trusted? Before a container crane ever touches a real shipping container, every electrical system, sensor, and mechanical component goes through a carefully planned series of tests. Imagine standing inside the control room as dozens of computer screens display live data from thousands of monitoring points. Every sound, vibration, and movement tells engineers whether the crane is truly ready for the world's busiest ports. The crane's electric drives, hoist motors, trolley system, and gantry wheels are tested one by one. Powerful hoist motors lift heavy test loads while laser measurement systems verify that every movement stays within extremely tight tolerances, often less than plus or minus 2 millimeters. AI-assisted monitoring software continuously compares real-time performance with digital engineering models, instantly flagging anything unusual. Most people never realize that today's cranes think almost as much as they lift. Next comes one of the most demanding challenges: proof load testing. Engineers suspend specially designed test weights that can exceed the crane's rated lifting capacity to confirm every structural component performs safely under extreme stress. Steel cables tighten with incredible force, hydraulic systems maintain perfect control, and every strain gauge records microscopic changes inside the structure. What looks effortless from a distance is actually one of the most carefully monitored engineering tests in the world. Safety systems face equally demanding examinations. Emergency brakes activate in fractions of a second, overload protection automatically stops dangerous lifts, wind sensors detect changing weather, and anti-collision systems prevent cranes from striking nearby equipment. High-resolution cameras, radar, and precision encoders constantly communicate with the control computer to reduce human error. Think about this. Hundreds of electronic decisions happen every second, often before an operator even notices a changing situation. Quality inspectors then perform a final inspection using laser trackers, digital measuring equipment, and detailed visual examinations. Every structural connection, bolt, gearbox, wire rope, and electrical cabinet must meet strict international standards such as ISO and FEM design requirements before approval. Modern factories achieve exceptionally low defect rates thanks to automated inspection and rigorous quality control, but no computer replaces experienced human judgment. Sometimes a veteran inspector notices a tiny detail that even advanced software overlooks.
Next comes one of the most demanding challenges: proof load testing. Engineers suspend specially designed test weights that can exceed the crane's rated lifting capacity to confirm every structural component performs safely under extreme stress. Steel cables tighten with incredible force, hydraulic systems maintain perfect control, and every strain gauge records microscopic changes inside the structure. What looks effortless from a distance is actually one of the most carefully monitored engineering tests in the world.
Now that you've seen how these engineering giants are built, here's something even more incredible. Every year, manufacturers around the world produce hundreds of large ship-to-shore container cranes and many more yard cranes to keep global trade moving. Together, these machines help transfer hundreds of millions of shipping containers annually through thousands of ports. Imagine trying to run modern international trade without them. It would feel like removing the engines from every cargo ship on Earth. China leads the world in container crane manufacturing, producing the majority of new ship-to-shore cranes used internationally. South Korea, Germany, Finland, and Japan also contribute advanced engineering, specialized components, and high-performance automation systems. Thousands of highly skilled welders, electricians, engineers, software developers, inspectors, and heavy equipment operators work together across this global supply chain. Most people never see these workers, yet their craftsmanship keeps world commerce moving every single day. Think about how far this technology has come. Early container cranes in the 1960s lifted far smaller loads and relied heavily on manual controls. Today's machines can lift containers weighing more than 65 tons, reach across some of the world's largest cargo ships, and use intelligent software to improve efficiency and safety. In just a few decades, these steel giants have transformed from simple lifting machines into highly connected industrial computers with wheels and cables. And this is where it gets truly extraordinary. Engineers are now developing semi-autonomous and fully automated cranes that use artificial intelligence, high-speed cameras, laser positioning systems, and remote operation centers located kilometers away from the port. Some operators can safely control cranes from comfortable offices instead of high above the dock. The future of heavy industry may look less like muscle and more like intelligence. Before we finish, here are 3 amazing facts. Did you know that some modern container cranes stand taller than the Statue of Liberty from base to highest point? Did you know that a single crane can cost well over $10 million, depending on its size and technology? And did you know that these giants often arrive at their destination partially assembled on specialized heavy-lift ships before crews complete the final installation at the port? What happens in just one day at a modern container terminal would have seemed impossible only a generation ago. From iron ore hidden beneath the earth to precision engineering inside world-class factories, you followed the incredible journey of one of humanity's greatest industrial achievements. Every beam, every cable, every weld, and every electronic sensor works together so millions of products can reach homes, hospitals, factories, and businesses around the world. The next time you see one of these towering machines on the horizon, you'll know you're looking at far more than steel. You're looking at decades of engineering knowledge, global teamwork, and relentless precision brought together on a truly gigantic scale. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.